Well, hello. In this video, I'm going to introduce one-dimensional graphics, and we'll discuss a bunch of things, but in the end, what I'm going to do is show you how to generate a plot, that in this case, we'll plot the sine function and cosine function and create a very professional looking plot that you could copy and paste into a document or presentation, publication, something like that. So let's go ahead and get started. I like to do everything from a script instead of the command prompt, just so that I can have a copy of what I've done in the past much more easily. So I open up my editor, and the very first line, I like to give this a name, and I copy the name in the first line. So let's call this, I don't know, demo 1D graphics.m. And so what I'll do is I'll copy that. I will do a save as, I'll do paste, and there we go. Now we're ready to go. And what's really neat is as I type, I can just press F5 and that automatically saves my code and then runs it. And you can see over here in the command window, when I hit F5, it automatically typed in the name of this script file so that it would run it. Next thing I like to do in my script file is just hit enter a whole bunch of times. I just like having this space down here, so when I start to type near the bottom, it behaves well. Okay, first thing in my codes, always initialize MATLAB. And I do three things here. I will close all open figure windows. I will clear the command window over to the right. And the most important one is to clear all of memory. Okay, let's just go ahead and plot something. Let's go ahead and plot a sine function. So the first thing we'll want to do is calculate function. So let's define number of points. Let's say 6 points in our plot. We'll create a theta array. This will be the angles at which we will calculate the sine function. And we'll use the linspace command in MATLAB. And the way this works is I give it a start value and a stop value. So we will go from 0 to 2 pi, and we'll do it with n points. And this creates an array theta containing, in this case, 6 points that goes from 0 to 2 pi. So if I hit F5, and then I go over to the command window and I type in theta, I will see all of these values. So we start at 0, we end at 2 times pi, and there's 1, 2, 3, 4, 5, 6 numbers in that array. Next thing I'll want to do is I will want to calculate the sine function. And I'll give this an F1, or I'll call it F1, because later when I calculate the cosine function, I'll call that F2. And so sine theta. And because I'm weird, I like to line up my equal signs. I think clean code runs better, and that's one thing that gives clean code. Also notice as I'm writing this program, I'm labeling everything, and I'm writing in just a few lines of code. I'll hit run and see what that does, and that's how I do. I never just write a whole bunch of lines of code and then hit run after all that. I type in 1 or 2 lines, hit run, 1 or 2 lines, hit run, and I kind of build it slowly like that. Okay, so let's go ahead and plot the function. Plot theta F1. And instead of hitting F5, I can also click the run command up here. It does the same thing. It saves the file, and then it also runs it. And there's my sine function. Now our goal here is to make this look good. And one of the first things I notice, and I notice a lot of bad things about this, maybe I'll just go ahead and say everything I don't like, and we can slowly fix this. I don't fix them all at once. I'll fix one thing at a time. But right away, when I'm looking at this plot, I see triangles and polygons. Notice how digital and polygon that looks. And anytime I see polygons in data, I immediately know there's not enough points that's been used. Now, maybe that's not always fixable. Each of these points might come from an experiment, and the experiment might take weeks to complete. And so, of course, we'll come away with very sparse data. In that case, when we plot, we want to be honest about that. And rather than connect it with lines, what we can do is make it a solid line. And let's do this. Watch what this does. Now, at everywhere we have a data point, we put a little circle, and we're being a little bit more honest about we only have data at discrete points. It's not like our data is actually polygon shaped. It's that we've generated it with very sparse data. Now, for us, we don't want this. We could easily add a lot of points. And so let's go up to something like 100. and plot it. And now that looks like a nice smooth sine. So that's great. A lot of other stuff I don't like about this. Notice there's some white space over to the right. Well, what the heck is that? We don't want that there. Or maybe we want it there if we're going to stick in a legend or put some kind of annotations here. We might want to intentionally put white space, but otherwise it looks awkward. Another thing, I noticed my function's crammed against the top and the bottom, and that's not such a big deal for a sine function because it just kind of goes up and touches and comes away. But we might want a little bit of white space above and below just to make that out a little bit better. I'm looking at the font sizes. That's probably way too small. I haven't labeled anything. I don't know what that is. And of course, we haven't added the cosine function. So let's go ahead and fix all of that. So first of all, let's get the cosine function in there. We'll call that F2, and that is cosine of theta. Let's go ahead and plot that now, F2. If we go ahead and run it, we only see one line, and of course it's the cosine. So what has happened is MATLAB went in and said, oh, okay, let's plot sine. Then it encounters the other plot commands and it says, oh, let's start all over. Let's erase everything and plot the cosine function. Well, we want to see both, so we have to tell MATLAB in some way, don't erase what was there before, just keep plotting on top of it. So one way we can do this, and there's a whole bunch of ways to create multi-line plots. I like to say, hold on, and then what it does is it freezes the graphics, whatever's there stays there. We'll generate this second plot. And then always remember to do a hold off, or weird things can happen, especially if those graphics is built into a loop and now you see the graphics from the previous iteration there, and it goes kind of crazy. Okay, let's run this. Now we see both lines. Well, now I might pick on the fact they're both blue. So if we were to have a legend, we might say, oh, the blue line is the cosine and the blue line is the sine. Well, they're both blue lines. So how do we tell the difference? So we want to make the lines look different. One obvious way is, let's make one of the lines a different color. We could make it red. That's great, but we have two problems. We have our colorblind brothers and sisters that now maybe can't tell the difference between those lines, or maybe this paper was printed in black and white, and again, we're not going to be able to tell the difference between the lines. Now, I love color, so I always like to have color, but I also like those lines to be distinguishable no matter what. So we can do two things at once. We can not only change the color, we can change the format of that line. We can make it a dashed red line. Now, if that's printed in black and white and the lines come out looking the same color, they're still formatted differently. Now, we haven't given this a legend or labeled those yet. That is yet to come. But I like doing it this way. Next thing I might pick on is those lines are probably pretty thin. If we copy and paste that into a document, those lines could easily disappear. So we want to make the lines thicker, but not awkwardly thick. So let's go ahead and make one of them a little bit bigger and play with that. And we have no idea, line width. I have no idea what number to give. Let's give it a 10 and just see what happens. We can always change it. Whoa, that is way too thick. Unless there's a reason to have an extraordinarily thick line, 10 is too thick. Typically lines are 0.75 to 2 unless you have a special reason. So we can type in 2 and that'll look pretty good. Very rare to go bigger than that. So let's go ahead and copy that line width command and paste that down there. Now both of our lines have that same line width. Okay, that's starting to look pretty good. Still a lot to fix up. We have things like font sizes, labeling, this white space here. So let's just go ahead and start to clean that up. So the next section in my code might be something like set view. And a quick way to get rid of the white space, in fact, to eliminate the white space that there might be around the entire plot, sometimes it'll appear on the left, sometimes top, sometimes bottom, we will just say axis tight. Now when we run it, MATLAB brings the edges of the axes right up against the function. And very often that's good enough. For me, when I have functions that maybe, especially when they spend some time railed against the top, like if I'm plotting transmission or reflection from a device, a lot of times transmission or reflection can either stay low for very long or stay high for very long. And I don't like functions to stay railed against the top because we might not see as easily what's going on. So I like to add a little bit of white space, top and the bottom, but not really white space to the left and to the right. So let's go ahead and dress up the y-axis. So we will use the ylim command, and we're going to give it an array of two numbers. And the first number will be the lowest value on the plot. The second number will be the highest value. Well, we know sine and cosine goes from -1 to +1. So what if we set our limits to -1.1 and +1.1? Now we see a classy and comfortable amount of white space above and below that plot. If we were to make that bigger, I don't know, maybe 1.7 and plot that, this isn't good unless we have a specific intent for all this white space. But all this white space in the top and the bottom is just wasting space. We really would like to stretch this function out over the full range of the plot so that we can see more. So I think 1.7 is way too much. So 1.1, maybe 1.2 is just fine. Now we might want a lot of white space above and below. Maybe we're putting in some kind of inset figure or some other kind of annotations and we want the space for it. That's fine. That has a purpose. But just to have that white space there not serving any kind of function, it's a waste of space. We don't want that. All right, now let's get into the labeling. Let's start with the x-axis. X-axis. And just to be complete, let's also do an xlim. And the default to make this tight, which has already been done, but I like to do this twice, I will make the left part the first number in theta, and the right part of the plot, or the maximum horizontal value, the last number in theta. So that really does nothing more than axis type, but you know what? If I change that, this would redo it, and it's a more robust code. So we can go ahead and run that and see that nothing has really changed. Okay. Next thing, I'm going to look at these tick marks. And I might want these to be in terms of pi. I don't like numbers like 0, 1, 2, because this is actually a radians number. I might want to see like 0, 0.5 times pi, 1 pi, 1.5 pi. So let's actually do that. So we're going to control the tick marks a lot more sophisticatedly. Is that a word? It is now. Okay, so I'm going to create an array of the tick marks. And in terms of pi, I want to go from 0 in steps of 0.5 up to 2 times pi. So my tick marks will be at 0 pi, 0.5 pi, pi, 1.5 pi, and 2 pi. The next thing is I want to create labels for each of these. So it's a string for each tick mark that will be put along the horizontal axis. And I know that my first one is 0, so I'll just go ahead and make that 0. If I want to get fancy, I'll make it 0 pi. That's only the first string. And also notice I'm using the braces here. Remind you, that's a sequence, not an array. A sequence is like an array, but each element in that sequence can be of a different type. I can have a string followed by a number, followed by a matrix, followed by something else. So I'm just putting in the string right now that when I display that as text will be 0 pi. Well, let's do the rest. And to make the code generic, we can set up a loop so that I can go in here and change my increment amount, and this will all still work. So let's go from 2. I'm not going to start at the beginning at 1 because I've already put in the first one here. So I'm going to go 2 all the way up to the length of t, however many numbers are in that tick mark array. Then inside the loop, I will say a curly brace m, and this is going to be a string now. So the first thing I'm going to do is give it a number. I'm going to use the num to string command, and then I'm going to be following it with a pi. You know what? I don't want the space there because it's 0 times pi, not 0 space pi. Okay, so I want to convert a number to a string. The number that I want to convert is the nth value in t, and then I want to control the formatting of that. And I want it to have a number dot a decimal, and that's it. So just 3 characters with 1 decimal. And so that's the ANSI code to do that. Okay, unless I made any mistakes, we're ready to actually set this into the plot. So we will say set, and we're setting the properties of the plot. Get current axes, and we're going to set x tick to t and x tick label to L. Let's go ahead and see what that does. I see a 0 pi, a 1.6 pi, 3 pi, and that does not seem to be working. And the reason it's not working is because I did a times pi here, and I need to divide by pi to get that back out. Okay, now we have a 0 pi, 0.5 pi, 1 pi, 1.5, 2. Okay, so that works. Well, one thing that's bothering me now, I don't know why I'm choosing to work on it now, the font size here is way too small. I just want to increase all the font sizes. So I'm going to go ahead and say set, get current axes, font size, and I'll pick a value. I'll pick 48 because I have no idea at this point what that number means. So we'll run it, and holy smokes, that's way too big. Yeah, let me bring this down to something like 18 maybe. All right, that looks pretty good. I definitely wouldn't go smaller than that. Remember when we publish something or put something in a document, we want our font size usually to be greater than 10. 10 to 14 is really where we want to be. And what we have to remember, if we create, let's say, a 12-point font here, we copy, we paste into a document, but then we reduce its size, that 12-point font is no longer 12-point, it's something now smaller. So we need to take that into account. So I wouldn't go any smaller with this, but this is starting to look pretty good. Now let's dress up the y-axis in the same way. And so I want to adjust these tick marks. So rather than retype all of my code, I'm going to go ahead and copy and paste this T and L loop is what I call it. And I do this all the time for my tick marks. Now there's no pi here. And in this case, I want to go from -1 up to +1. The little plus sign is not necessary there, but I like doing that. It gives it symmetry, I guess, with the -1. Makes the code a little bit easier to read. And I'm going to initialize this to nothing. So we need to go through all of the numbers. So that means we'll need to start our loop at 1. And we're not doing this pi thing. I still like this same formatting, so we'll keep that. We'll get rid of our pi. And we need to change this to y tick and y tick label. Let's go ahead and run this and see what we're looking at. All right, here's where we are. We have a 0.0. What we would like to do is have the same number of significant digits. So if we didn't do this, remember we had a 0.5 and then all of a sudden a 1 down here. And so the position of the digits is sort of dancing around, and it takes somebody's eyes an extra second or two to digest what's going on. But if we can keep a consistent number of significant digits here, it's much more pleasing to the eye, with one exception, and that is the 0. We don't want to ever say 0.0 because that implies that it may not be exactly 0. It might be 0.03 or something like that. So our 0 really needs to be truly 0, and I think the best way to handle that is just to handle that case specifically. So if the nth value of t is 0, I'm just going to make the nth string in L exactly 0. And then, of course, for anything else, I'll do what we just did. And now we'll run this. And I think that looks really good. The last thing is we have not labeled our axes yet. So let's go ahead and say, whoops, X label. I'll get that type correct eventually anyway. All right. So the x-axis is our theta. And for fun, let's say angle. And then we'll give it the symbol theta, and we'll remind ourselves the units is in radians. In case the pi is down here, didn't make that obvious. Let's go ahead and run that and see what that looks like. Okay, angle, we see theta and radians. Maybe we want to label the vertical axis. I'm not sure what we would put there. Maybe we just label it as function. Maybe we label it as sine and cosine. I don't know. But maybe we could just do that in a title. So let's give it a title instead of a y label. So this is sine theta, and it is cosine theta. And let's get rid of the space. Let's run it, see what that looks like. Sine theta and cosine theta. One thing sometimes I like is the title font to be a little bit bigger, but here it's bolded, so maybe that's not completely necessary. But if we did want to change the font size, here's how we would do it. We would just say font size and something bigger than 18. Let's try 22. And now that's a little bit bigger. And that's certainly something that you can play around with to get exactly right. So this is really it. I think there's not much else we could do here. To get this into a document, I will come down and say copy figure, and then go into that document and paste it in. And when we do it that way, this gray background does not make its way into that. So we don't really have to worry about the color of the background here. It'll go in as transparent. We can also play around with the size of this, but if we shrink this down, the font sizes, notice they still say stay 18. So at this point, that looks kind of silly. Again, that also looks silly. It's an amateur mistake for people to insert a plot like this as full page, thinking, oh man, my professor's going to love this. He's going to be able to see everything. But that's very amateur. Your graphics should always be as small as possible, such that everything is still easily readable. And you can get this by going into your high-end magazines like Nature or Science, and you don't see a simple plot like this being full page. This would be a half-page plot if something like that were in there. And so we can shrink that down, and something like this is still very readable. I might reduce the font size a little bit, but that's a pretty good plot. There's really not a reason to make it bigger. On my day-to-day activities, I tend to just like my figure windows to be bigger. But when it comes time to pasting it into something, I'll reduce it down as small as it still looks good and is easily readable. So that's it for 1D graphics. I hope this helps you.